Okay, cool. Um, so yeah, so the title of the talk of the program is the projected Bellman equation in reinforcement learning, and the overall objective is to try to figure out why Q-learning works, because it does empirically. I have no answer to that. So I can tell you all about the projected Bellman equation. Why Q-learning works in practice is a mystery to everybody. It's really, really something. Despite all the theory, it's really, really no theory to explain why you get such good results so often with the algorithms. And so I'll explain all that, where this comes from. So this is partly a tutorial and partly some very new results. The table of contents, this is based on a tutorial or a lecture I gave at Toulouse last summer for a bunch of people where everyone was immersed in Markov decision processes and MDPs and all that. And I think that this audience is much more varied. So I'm probably going to skip the second order methods right there and just jump from Watkins to the new theory on projected Bellman equations. But you'll have this slides if you're interested. There's some really fun stuff there. But I just don't think I'll have time for it. So I should go slow. Now, some background, that's the thing, right away I have a problem because maybe half of you don't have this background. If you're at the summer school, I spent an hour and a half on this and there was homework as well. But there's something, there's something called stochastic approximation where the goal is just root finding. And the function of interest is the expectation of something, all right? And the ODE method is to first pose an ordinary differential equation. If this is globally asymptotically stable, it's going to converge to a stationary point. You could do an Euler approximation, but you would still have to compute this expectation. And instead, you follow Robbins and Monroe, and you use the stochastic approximation algorithm. So you just go through and you remove the expectation, just plop that in. And this could be Markovian or ID. And the theory, I mean, partly because of reinforcement learning, the theory of stochastic approximation is advanced tremendously in the last decade or two. And so, I mean, it used to be, I mean, if you look at even Borkar's book, who is the best book on stochastic approximation, I think, he essentially assumes this is independent, identically distributed. Not really, but his assumptions really almost imply it. You don't need any of that. I mean, this can now depend on the parameter. It could have, I mean, it could be almost anything. Now, here's a funny thing is that in some circles, it's fighting words to say that RL is related to this at all. You can get some people in the RL community angry because I have experienced this. Some people can find it territorial. But if you go back to the literature in the earliest days, even in the 80s, Sutton pointed out that there was a connection with stochastic approximation. And then Michael Jordan and Johnson Siklis in the early 90s made it explicit. So this is well known. I'm not pretending that I invented this connection. It's, most people know, but a lot of practitioners don't. And so they're missing out on a whole bunch of wonderful ideas. Now this point of view here, it says here, ODE method using a different meaning than in the 70s. The idea of looking at the ODE and then coming with a stochastic recursion, that was a point of view in Russia in the 70s. But then unfortunately we looked at this backwards. So in the West, basically the dogma was you look at a complex algorithm, you come up with a ODE approximation and use that for analysis. No. It was a mistake all along. You start with an ODE, you design it so it has nice numerical properties and particular stability, and then you come with an approximation that gives you an algorithm. And you don't have to use an Euler approximation. You could use some other second order, I mean, all these clever ODE approximations you might use, and to get a more better behaved approximation here. All right. So that's background I can't cover, but it's so simple that there it is. I'm doing an ODE approximation. But it's funny is I went back and reviewed this again last week because of the summer school. If you go back to Sutton's papers in the 80s, he writes down these equations without pointing out stochastic approximation. He doesn't reference Sutton, the literature at all. He calls this the reinforcement signal in all those old papers in the 80s. It's sort of sweet. So there you can really see the connection. But this is called the step size sequence. In those early papers, it was always constant. But that's, I would argue, well, in my tutorials last week, I argued that's a mistake. In RL, you would never want a constant step size. It doesn't make any sense. Just a cheap vanishing step size is best. That's another tutorial. All right. Now, in terms of resources, there's chapters 4 and 8 from the new book. So CSRL stands for Control Systems and Reinforcement Learning. Each one of those is a link to a book, so you can get a PDF copy of the book. I'm not going to get into that. So this paper has been under review for 4 years, and finally has appeared in Annals of Applied Probability. And in those 4 years, it evolved, and now it can handle like state-dependent noise and all sorts of parameter-dependent noise, all sorts of things. And then Borchart's book, even though it's hard to read, is a really wonderful resource. Especially chapter 2 shows how easy it is to get convergence of stochastic approximations. So there's some resources. In terms of applications to Q-learning, temporal difference learning, SARSA, blah, blah, blah. Chapter 5 of this book is deterministic, and 9 and 10 are the traditional Markov decision process setting. That's the setting of this lecture. Okay? And this lecture is really, the new stuff is this paper that just appeared in the Transactions on Automatic Control, which is the title of the talk. And that, there's an archive paper that's basically a summary after a tutorial in Nancy several years ago. And it has all sorts of fun new stuff as well, which I won't get into. But so these are worth looking at. Now, motivated by Aditya, because it's terrible not to give some other background. Related is, number one, is a paper by De Farias and Van Roy that I wasn't aware of until after I'd submitted my projected Bellman error equation paper. They have this weird, this paper with a terrible title, Approximations of Fixed Points for blah, blah, blah. There's some ideas there that are related to my talk, and in particular, after the fact, their way of getting fixed points, their methodology is the same as my methodology to get fixed points. Okay. There's a paper here, which I do refer to in this paper, and it's roughly related. It's hard to talk about really. It's complicated to discuss. But now there's this paper which I'm not proud of here with 2 Portuguese co-authors. It's like my 5th most cited paper, but I don't recommend it. And then this is other paper which is related to this. So I'll talk about this at the end. It's basically showing the existence of a solution to the projected Bellman equation, sort of. It's really a solution to a fixed point for something that I'm going to call epsilon optimistic SARSA. I'll define that at the end of the lecture. This paper basically takes the standard Q-learning algorithm and projects one of the nonlinear term, and is able to then get bounds. So there's no existence of limits or stationary points or anything like that, but they get bounds. But this, I'm sort of making fun of this because it's sort of semicircular conditions for convergence, because basically the paper takes the proof of convergence for TD learning and says, if all those assumptions really would hold for Q learning, we'd have convergence. But those conditions never hold for Q learning. There's no example in this paper really at all. And then this follow-up really has a couple of examples, but still nothing. So all of this is really saying that this whole topic of Q learning even having any kind of possible limit point. So first of all, Q learning is stochastic approximation. There's a theta star we're trying to compute. There's no theory for the existence of a theta star until this paper, except there's the tabular setting of Watkins, and the extension to binning of Jordan and all back in, another century. But that's that. So it's really exciting to get something. And again, for nonlinear function approximation, so this is all for linear function approximation, including my talk. If you want to go to nonlinear function approximation, the only result I'm aware of is my paper with my grad student 6 or 7 years ago. And there you need a matrix gain. So if you slap in a matrix gain, you can get convergence, even with like a neural network architecture. Yep. No, I don't know about uniqueness. Well, you'll get to that. I'll show you all the assumptions and conclusions in a bit. Okay, so Caillou is back there. So I'm leaving out all this fun sort of zero variance theory with Caillou. I mean, basically there's exploration that comes about in these algorithms, and people typically like put in IID shocks for exploration. And in many contexts, that's a mistake. You can design exploration so that the resulting variance in the algorithm is zero. And I can't even define that. But there's lots of fun stuff. And it's funny, I made a list of publications here, and I realized that, I didn't want to use up too much room. There's 2 NeurIPS papers that I left out. So there's some really fun, I had a blast with this guy. I'll be sad to see him go. And he's graduating, he's on the job market, and he has funds for a postdoc. Grab him before he disappears. Okay, so Q-learning. So this, I forgot where I stole this from. I think it was a lecture by Richard Murray, a co-author with Carl Astrom, Give It a Survey and Control. And the point of showing this, as I said in the tutorial, the control is not single objective. All of RL is obsessed with optimal control with a single objective, almost all. And of course, that's not really what we're going to do. But it's still worth studying a single objective problem because you're building tools that will be useful in multi-objective problems. Okay. That's that. I'm not going to go into what this means. But here it is. So how many people know about MDPs? I don't know my audience at all. Yeah. Okay, good. Only a few didn't put up your hands. Maybe you're shy. But anyway, I've got X as my state process that I want to control. And then I've got an input. I'll call it an action sometimes for people who like that. Inputs and actions are the same thing. And if I want to be in a general state space, I have to talk about going from a state X to a set A. So for any subset A in my state space, the probability of going from an initial state and an input U, and also condition on all the prior history, is given by this control transition kernel. Okay, so it's a transition matrix if the state space is finite, and then I can just replace A by a point. I'm just looking at the probability of going from one state to another state. I've got a cost function, and for simplicity here, I'm going to look at the discounted cost criterion, even though I can't stand the discounted cost criterion. I much prefer average cost or total cost, like cost to some set or something, the shortest path problem, things like that. But this is, it's much easier to analyze this algorithms designed for this criterion. The equations are simpler. So this is the Bellman equation. And this is the value function, tweaked a bit from what Bellman would have looked at. Because Bellman wouldn't have conditioned on the initial input. He would have taken the minimum overall U from 0 to infinity. This is the minimum of inputs, U1, 2, 3, 4, ignoring 0. But the reason for doing that is this. So Watkins thought of this, back in beginning of time. By looking at the Q function, you get 2 things. One is that the minimizer of the Q function gives you the optimal feedback control under very general conditions, number one. So Q star is really what you want to get the optimal control. But maybe even more important is this. You've got an expectation of a minimum. If you looked at the value function that Bellman looked at, you'd have the minimum of an expectation, and you'd be screwed. All of the Monte Carlo methods would disappear outside of deterministic control problems. And so that was really the breakthrough in Watkins' thesis. It was to, I mean, that was, I think, more important than the fact that this is really what you want. Yeah, so in TD learning, where you're just looking at a fixed policy value function, that issue didn't come about. That's why all of Sutton's work on TD learning looked at the value function, not the Q function, because you didn't have to worry about this nonlinearity. And this nonlinearity is what makes this equation hard, to deal with. It really is annoying. It's what, it's what's really stopped us in terms of theory. Right? It's this right-hand side, if you think about it as a functional fixed point equation, think about Q star. I'm looking at all functions. It's a function of Q. This is an operator in functions. It's concave. It's a minimum of linear functions. And just imagine how weird that is. I've got Q is a concave function of Q. Does that sound familiar to you? Not to me. It's an ugly fixed point equation. The contraction there is what makes it analyzable, why you can prove that value duration works, things like that. But as we'll see, it's really hard to analyze in the way Q learning is formulated. All right, so here it is. I'm gonna derive the stochastic approximation algorithm, the standard one. I'm going to use Fn to denote just the whole history of observations up to time n, right? And so that is something that's a function of the history up to time n. So it really can come out of the conditional expectation. Same with that. Xn and Un are observed at time n, so that's not. But that here, I'm taking a conditional expectation because, see, I've got a conditional expectation right there. That's all I'm doing. So I'm reinterpreting this equation as something that I can, begin to come up with a root finding problem. That's my goal. Right? Okay, so there's a root finding problem. If I look at Q star and think of that as theta, Q star is my theta star, in terms of stochastic approximation, in a way. Except it's a conditional expectation. So sorry about that. Now, whenever you see an underbar, it just means I'm taking a minimum, all right? So over and over again, you see some function, h bar of x, it just means h is a function of two variables. I'm taking the minimum over u. We use the input or action. Okay, now that's what I'd like to solve. And here's what you do instead. You pick a vector, a random vector. Well, first you come up with a parameterized family of approximations. So the theta there could be weights in a neural network. Look at a parameterized family of functions. And I set this up as a root finding problem where f bar of theta star is this expectation here. And so why would you do that? Well, it turns out that this is equal to 0. Suppose that suppose that Q star was actually in this family. All right. Then for that particular theta, this condition would hold if and only if this were 0 for every zeta n that it's bounded and in the a function of the history up to time n. Right. But what we're doing is we only have d variables because we're in RD here. So I need d constraints. And so that's why you end up choosing a random vector here of dimension d. So it's a real hack. You can give it all sorts of fancy names. So that's called the projected Bellman equation. So you can give it a fancy name. You can call it the Einstein-Hamiltonian cure of cancer equation, but it's still a hack. And no matter what anybody says, nobody's convinced me it's anything but a weird hack. It's not, I mean, it doesn't have the beautiful interpretation of that you might like, but yeah. No, it's vector value here. Yeah, this is a d-dimensional vector. This is a scalar in brackets. That's called the temporal difference. And then you just hit. Oh, yeah, that's scalar. Yep. And I just dropped it in here. That's a scalar.
Scalar equation is solve? Would you make it into a vector equation?
No, it's infinite dimensional, right? I mean, it's not scalar equation. I mean, yeah, I mean, if I'm in a general state space, it's infinite dimensional. I'm trying to find Q, right? So
Okay.
Q star could live in some massive, even for a finite state space, finite action space, Q star lives in this high dimensional space. And so I'm basically looking instead at a little d-dimensional root finding problem. Yeah, Q star is a variable, and it's in a high dimension. Yeah.
You multiply by size or?
Yeah, you see this? So again, Q star could live in a space, like suppose there's 100 states and 100 actions, then Q star lives in 100 times 100, 10 to the fourth dimensional space. So I've got a, 10 to the fourth dimensional root finding problem here, But what you end up doing is you say, well, I can't do that. So let's take D to be 100. And now I'm looking at a root finding problem of low dimension. Okay, well, this is a scalar, and that's a random d-dimensional vector. And that's what it is, and that was observed by Tsitsiklis in '93. That this, this is nothing. I am not creating this. I'm just a reporter. But this is what pisses people off. I'm not going to name names, but some people in the ORL community don't like being told that you're solving a root finding problem and applying stochastic approximation, even though Tsitsiklis and Jordan said that in the early '90s. Yeah, so like I said, I want to get that cut off, but yeah, so that is a projected Bellman equation. Just look at the definition. That's how it's defined in Sutton's book and other papers. It's just the definition. You take, that's called the temporal difference, and you multiply by this random vector, which is called the eligibility vector or eligibility trace for some reason. And there's a canonical choice for that I'll give you in a second. Yes. Why? I mean, it's just that, there's sometimes, it doesn't imply anything, So this implies, so if Q star was in the function class, then this solution, this equation would be solved for that optimal choice of theta, right? But the reverse, nobody's found an implication about if this is 0, does it say anything about the policy performance? Anything at all, It's amazing, but empirically, I personally find it works so often. It's just an amazing mystery to me. And this was a big, I helped organize a session spring of 2020. It was fall of 2020. It was really disappointing because of COVID knocked it out. But we had a big whole semester in Berkeley on this topic on Q learning. It was the whole semester was discussed about the meaning of this equation. Did it imply anything? And there was some debate in the beginning, and by the end, everyone put up their hands. There's just no conclusion you can make. It's really cool. There must be. I mean, it can't be just luck that it always seems to work so well. That when you solve this, you so often get a good control solution. No, except for in the tabular case. So what's called the tabular case is when you have a basis that spans all functions. And not only that, I mean, very special structure. Well, then you're spanning all functions. And if you set things up right, then you do have a unique solution. And then you're not approximating anything. You're solving the DP equation. But that's not what, normally X lives on maybe a general state space. We're talking about a problem in robotics or something. And we're taking this to be some neural network. And you play around with different neural network architectures. And you find that, a couple layers and you do a good job. It's really cool. I just can't wait till somebody figures this out. Right, all clear? No? Yeah. No, because I've got D unknown, So I want D constraints. Yeah, well, yeah, I mean, yeah, the theory demands it's d-dimensional. And in fact, I'm going to give you the typical definition in a second. Yeah. Well, you can imagine then you have more constraints than unknowns. And so, you'd end up, you could end up with problems. You'd, yeah. I mean, it might be interesting, too, because I mean, that might not be a solution, but you could look at a minimum norm. Yeah. And that would be fine. Yeah, I mean, it could be interesting. I haven't seen that done. But anyway, I've never seen it done because in the way Q-learning is typically defined, you're not given this flexibility. Typically, you define the eligibility vector you take the Q function, you take its gradient, and you evaluate that at the current parameter estimate. And that's the definition. You don't have to define that. But it leads to, it leads to nice analysis sometimes. And also, that's what seems to work. You really find that it's nice. And you'll see why in a moment. I mean, why it's appealing. In the tabular case, it's clear, which I'll define that in a moment. The tabular case. All right. Now this Q0 isn't something you'll normally see. It's just that in TD learning, when you make this definition, that's called TD0 learning. So I might as well use the same definition. And I'm really emphasizing the fact that I don't have to use that. I could do what you do in TD learning, which is you take this and you put it through a low-pass filter. And that's what happens. The TD lambda refers to the parameter of this low-pass filter. It's exactly stochastic approximation, the standard Q-learning algorithm. This again, standard, not mine. This goes back to to Watkins. And this F here is a product of this eligibility. This what's called again the temporal difference times the eligibility vector. And I told you that this lower bar refers to a minimum. This is just a different representation. So this really is what I've done here is plugged in the minimizer over all U. Okay. Right there. So whenever you see this phi theta of x, that's what's called the epsilon, the Q greedy policy. I'm taking the policy which minimizes this. So if Q theta were Q star, this would be the optimal policy. All right. Now the inputs chosen for exploration. So I forgot to say that. What's so damn cool is that this holds for any input as long as it's non-anticipative. UN it may be a randomized function of the states up to time n. Then this equation holds. So I have a choice on what inputs I use for training. And almost all of the analysis, the input is chosen for its IID, independent, identically distributed, completely independent of the parameters. That's what's done in all the theoretical papers. Nobody does that in practice. It's just this infinite separation between theory and practice. It's wild. So all the sample complexity bounds you'll see for what's again Watkins Q-learning, which I'll define in a moment. It's all for the case where the input is just independent, identically distributed. I bet it could be extended, but people just haven't had the energy. Yeah. All right. Now with linear function approximation, things get a little bit prettier. So if, way to go. Yeah, so if the function class is linear, just meaning that Q theta is theta transpose psi, where psi is a d-dimensional vector of functions. Then this eligibility vector just becomes the basis vector evaluated the current state in action. And nothing else really changes much. It's just the same thing. But this helps a lot because now the product of zeta n here and this gives you this big, obvious negative definite term, which makes you feel happy. It makes it look like it's going to stabilize something. All right. So it'll be clear in a moment. Well, actually, yeah, right there. So you can write down f bar of theta for the oblivious policy. You can write it very simply. I've got a matrix here, d by d matrix here times theta, which is this, part of the temporal difference. And I've got zeta n times that difference. Well, zeta n again is just psi. So you see that I've got a psi times psi transpose there in the minus sign. Yes, something negative. So I've got like an autocorrelation matrix sitting right there. And then you might think, I've also got this times that and a contraction term. So the negative term should somehow dominate and create some sort of stability. But no, that's what screws everything up. The fact that that input, that greedy policy there has nothing to do with the UN there. This matrix doesn't have to be Hurwitz. Lots of examples show it can be. I know this is a time-varying system. I mean, it's not a linear system, I know, but still it'd be nice to know this was Hurwitz for each theta, and it's not. Lots of examples that show with oblivious training, this matrix can be anti-Hurwitz for every theta, and the algorithm you run it is sort of consistent with maybe some false intuition you might have. This blows up. Right? That's been known for a long, long time. Yeah. So, and then B is this product of the cost function and the eligibility vector. Now, if it wasn't oblivious, if the input depended on the parameter, then the expectation would depend on theta here and here, and things would be a little bit more complicated. But, Oh, cool. Okay, Watkins algorithm. All right, so it's really worthwhile going through this. All right, I've got a linear function class, and I've got the most boring basis in the world. I just take the ith element of the basis to be an indicator function, that x equals xi, u equals ui, xi, ui, I equals 1 to 1,000,000 is just an enumeration of all the state action pairs. This is Watkins' algorithm. And it was really fun in the discussion last week during the school. Somebody pointed out that in the example we're looking at, we had a complete basis, right? And if you ran Q-learning, it would blow up. And it was all indicator functions of sets. There was a complete basis. You could span all functions. But you plug it into Q-learning, it blows up. It's unstable. Actually, I'm going to give that example in a moment. So it's really important that you choose this very specific tabular basis, and then you get stability under very mild conditions. One thing, though, is it sucks. So people complain all the time that Q-learning is slow. It's a terrible algorithm. It's very inefficient. That is the best example of why the people came to that conclusion, because they didn't understand the theory of stochastic approximation. It really is the only reason. So the fact is that Watkins proposed a step size rule, the step size in the algorithm, which was like 1/n roughly. And that's it turns out a terrible choice. So if you choose a different step size rule, you'll get very nice convergence. So this is just saying, in fact, basically this is saying the mean square converges slower than 1/n. In fact, if the step size, if the discount factor is close to 1, you can get the convergence rate of the mean square error can be 1/n to the 0.000001. It can be arbitrarily slow if you use Watkins' step size rule. But if you go and look at the stochastic approximation literature, you'll see, oh, shouldn't do that. So it's really it's worth knowing the theory. Now, this is known as the asymptotic variance. And people see infinite variance, they immediately think high volatility, and of course not. It just means that it doesn't move. So basically, if you take Watkins' algorithm off the shelf, just apply the rule that's given in his paper, and you look at a histogram after 1,000,000 iterations, you'll get something that looks sort of Gaussian, as you might hope, because you do have a central limit theorem in these things. But the actual theta star is over here, so you're just stuck. You can imagine 1 trillion samples later, it may be still stuck. So it's a bad step size rule, that's all. So even though convergence is trivial, you've got to think more for rates of convergence. All right, and I'm not going to get into this much, but if you crank up the gain, or you do something called relative Q-learning, you can take this very slow convergence and make it super fast. I can't get into this at all. Just time. Just go and read the book or these references. Yeah. So for the essay tutorial last week, basically what's proposed is instead of a step size rule of like 1/n or something, you should take a constant of n to the row where rho is less than 1. And you'll see lots of oscillations. You'll see it go, wham, 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 just crazy oscillations. But then if you just average it, you get the optimal rate of convergence. 1/n rate of convergence mean square error. And not only that, this sigma squared is optimized as well. It's minimized over all algorithms in a given class. Okay, so just a simple hack like that, you get the optimal convergence rate. So never, never, never this. Watkins algorithm, you look at the number of times you visit each pair, state action pair, and you look at 1/that for the step size rule. No. All right. Now, besides all this, what I'm going to get to at the end is, this joke picture I always use, that what would you do if you were a mouse trying to learn how to find cheese? You would see a cat once or the poop once, and you'd learn to not go there again, And it would end up being a very efficient algorithm. Hi, cat. Hi, poop. I learned the optimal policy. And so that's actually what happens. Practitioners know that, and that's why they come up with these training rules that depend on whether you've seen the poop or the cat. And you visit state action pairs less often when you see something nasty, and you get much better efficiency. Okay, so that's the big message of today's lecture. But if I had time, I would go and look at second-order methods to improve efficiency and so forth, and stability. But we don't have time for that. So I'm going to go straight to the intelligent mouse. And this is just a joke. This is what you're missing. How matrix gains can stabilize. Okay, so basically what I want to do is I want to look at, a big challenge is that I don't know if a solution to this exists at all. And nobody has known that forever and ever and ever, except for the tabular setting. It's been open. And there's an inverse, there's an A matrix. It's gone now. But it's needed for analysis and knowing that you can get a fast convergence rate. It's for these second order methods. It's the Jacobian of F bar. Right there. We don't know if that exists. And so that's a big topic. But the other topic is stability, because I mentioned the examples where you run Q-learning with linear function approximation, it just blows up. And this is just showing simulations. In one case, I look at this linearization over here, and I find it has eigenvalues in the right half plane at theta star. But notice they're complex, and if you run the algorithm, you get this oscillatory behavior that blows up, consistent like with a linear system with complex poles on the right half plane, if you know anything about state space control and all. So that's sort of fun. And over here, I've got a different set. I've got real poles in the right half plane, and I get this blowing up like that without the oscillations. They're not complex. This is from this famous example of Baird back in the 80s for TD learning, and you can extend it to Q learning. And so I want to address both topics: the stability of Q learning and the existence of theta star. I will not address uniqueness, and I will not address convergence, because it's completely open. Nobody knows how to prove convergence. It just does. Okay, so again, the elegant theory for Q-learning, the training is oblivious. And again, the mouse only has to see the cat once. That's how you'd really do training. So here's what's done in practice. So you take a randomized policy like this. One is to take U to just be the greedy policy with probably 1 minus epsilon, and it's probably epsilon do something random, just completely oblivious. Alternatively, you can look at this Gibbs policy where you take some large constant kappa and you take the probability of choosing the action U given the state X, is you just plop in the Q function and plug in this minus kappa, and that's the probability. The Z there is a normalizing factor. So when you sum over U, sum over U, you get 1 to make this a valid probability mass function. Okay, so these are both fail in terms of analysis. So in the first case, you get a discontinuous vector field. And yes, Ben Meyn in Switzerland, I think he's at EPFL, has beautiful work on stochastic approximation with discontinuous vector fields. But you can imagine it's at least as hard as ODEs with a discontinuous vector field. It's just awful. Now, this fails as well because I haven't talked about this, but stochastic approximation theory, all of it depends on global Lipschitz continuity, and you don't get that. Because what happens is when the norm of theta goes to infinity, this becomes degenerate. And that means that you get an infinite. I mean, if you take the gradient of the F bar that pops up and look at its max, it's not bounded. So you don't get something uniformly smooth like that. So that's part of the reason that that's been no success, is that the stochastic approximation theory failed. So one little hack fixes it. You just choose a inverse temperature, it's called here, which depends on theta, and it's just meant so it doesn't blow up, keep it bounded. That's it. That's innovation number 1, to make things smooth. And so basically something that, this is linear in theta. I'm going to look at linear function class. And so I'm divided by the norm of theta, so I get something bounded. Okay, so now the Lipschitz condition continuity will hold. And I just make sure it's big everywhere else. Theta bigger than 1 is just arbitrary. I just want it to, to be roughly 1 over norm of theta for big theta, and then smooth everywhere else, and everything's good. All right. Yeah. Okay, so then I've got, again, the Lipschitz continuity that I need. That's step 1 in stochastic approximation, making sure that the vector field F bar, its gradient is uniformly bounded. I wouldn't get that with this. It wouldn't even be differentiable with that. And then this gives me everything. Okay, step 1. Now, step 2, it was really annoying having to deal with getting my greedy exploration from this alone. In the end, it just was easy to tack on some extra noise. So I've got this, which is a smooth approximation to epsilon greedy. And I got a convex combination of that and something purely IID and purely exploratory. So this is something that maybe just samples all possible feasible states. Inputs. Clear? And I don't think it's needed. It was just, it made the analysis much, much simpler. Because in the theorem, I was able to say, crank up kappa naught, make it sufficiently large, and then choose epsilon small enough for the theory. And there's explicit bounds in the paper. All right. All right. And then again, linear function class. And here's the key assumption. I need that if you take the, when epsilon equals 1, I kill this off, I'm oblivious. That's what I'm saying you should not do. It's not stable. In lots of examples, it's not going to work. But in that extreme case, I want this autocorrelation matrix to be full rank. Right? That's number 1. Again, that's with UN just oblivious. Oh, that's right. And there's a unique invariant, probably a mass function for the state input process. Right? So I need that. I need that to define my F bars and all of that. Not a big assumption. But then if that holds, you can show that for any theta, any epsilon positive, between 0 and 1, I should say, there's a unique probably mass function for the joint process again. And the new autocorrelation matrix is full rank. So that's a lot of work right there. Yep. New W. Oh, yeah, no, it's just a distribution. Yeah, new W is some probably mass function on inputs, yeah. And I mean, I know most practitioners would take it to be full. It's full support on all possible actions. You can imagine that might not be feasible. The only assumption I really need is this rank condition. All right, and then you can show that ends up all the autocorrelation matrices are full rank for any epsilon between 0 and 1, right? Strictly between 0 and 1. So as epsilon goes to 0, typically this will become degenerate. Typically, not always. In interesting problems, it will. All right, and then you get this wonderful result. There's a epsilon that depends on gamma for this problem. And number one, you find that this mean flow, the thing that you look at, step one in the construction of a stochastic approximation algorithm, it's not globally asymptotically stable as I'd like, but it's ultimately bounded. The trajectories sort of go exponentially fast to a compact set, and then they buzz around. I have no idea what happens. And number two, there's at least, oh yeah, and the proof is just looking at a stupid standard norm as a Lyapunov function. So basically there's some delta, so which I get exponential drift for the mean flow whenever the state for the ODE is large. Okay, so that implies the same property holds for the stochastic recursion. I mean, not this, but it implies that you go into a ball of radius 1 over epsilon and bounce around. And then there's an existence, at least one solution to this projected Bellman equation. And the proof is similar to the stability proof. You know, you define this function, T of theta, and you can convert the root finding problem to a fixed point equation. So it's going to go, we started with a fixed point equation, now we're coming back. And from the stability proof, you can show that it maps a compact set to itself. It maps a big ball of radius 1 over delta to itself. And you can apply the Brouwer's fixed point equation proof. You know. And so that's how Farias and Van Roo, like I mentioned, for another problem, but they showed the existence of a fixed point equation for a different problem, but closely related. I found that out later. Okay, cool. So, yeah. Now, I'll just quickly go through an example and quit. So this is a famous example for which you can come up with, a full basis. Everything's perfect, yet the algorithm is unstable. So yeah, this is a picture I showed you again. I can't go to the details, but this is exactly the setup of BARD, where it's TD learning, not Q learning, but you have that. And if you look at so A star is the linearization of the mean flow vector field at theta star. If you apply an epsilon greedy policy, this doesn't mean anything, but it's just to give you some idea of what's going on. See, we want A star to have eigenvalues in the strict left half plane, in the complex plane. And what happens if epsilon's too big? No, you don't. So the linearization at the origin is unstable, and that's just a red flag. All right. But if you make epsilon smaller, you can see that with discount factor 0.9, there's a sweet spot right there, and 0.95, it's there. When gamma is 0.99, you can't see it, but it's really negative, I promise. The theory says so. And so that's that. That's just an example. And this is what the sample paths will look like. I mean, if you take, this is an epsilon 1/2. With gamma equals 0.95, you run Q learning, wham, it converges, quite nicely. Because this is only 10 to the 3. That's very short for Q, these sorts of algorithms. And boom, for gamma equals 0.99, it's unstable. So you would need a smaller epsilon. 0.5 is too big. If you make epsilon, 0.2 works, and anything smaller, you get stability of the algorithm. So even though you couldn't see anything in that plot, I was showing you the eigenvalues and all that. You couldn't even see if it was negative or not. It is stabilizing if you take epsilon small. So so I love this. I mean, the fact that I mean, for me, using epsilon greedy policies in training was purely about efficiency. That's all. Or if you're doing online control, you're trying to learn on the fly. So you're trying to learn a policy for flight control as you're flying the airplane. I don't recommend it, but but it was mainly for efficiency. But the fact that it stabilizes is such a cool message, and that's not was not known until last year. Yeah. Yeah, I got a formula for that. Yeah. So yeah, so the if you do things right, the mean square error converges like 1/n, but the constant in front is like 1/1 minus gamma. The variant. Yeah, I can give you explicit formula. Yeah, yeah. But you can get rid of that. That's the next slide, I think. Yeah, I'm about to give it. So yeah, so if you average the parameters, so you take the output of Q learning and then you just do a simple average, then you'll end up with a 1/n convergence rate, but the constant in front is like blows up as gamma goes to 1. If you play with this a bit, you can get rid of this dependency completely. So basically what you do is you look at what's called either the advantage function or something called relative Q learning. What you're doing is instead of estimating Q star, you estimate Q star minus some function of X. And in advantage, this is a value function. In relative Q learning, this is like the mean of Q star. Okay. But since it doesn't depend on you still got the optimal policy. All right. And if you use either of those techniques, you get rid of that. You get something uniform in gamma. It's really sweet. Yep. What's that? Oh, I see. Yeah, exactly. That's where it comes from. So if you look at relative Q learning, it's inspired by Barkar's algorithm, where you subtract a term. We actually, no, I don't have it here. I don't. I thought I maybe had. Yeah. Now, if somebody can give me a better name for this, let me know. I just cooked up this name on the fly. Epsilon optimistic sarsa. So this pops up in my paper without a name. It was just sort of a comment in the paper. And I realized for a lot of people, this is what they want. So you basically run what's called sarsa. This is sarsa, where instead of a minimum here, I just plug in the input. That's a sarsa algorithm from way back when. But with U defined by one of these epsilon greedy policies. Okay. So everything I said applies to that as well. And if I, do the trick here of sticking in something to, I can also get the variance to be small as well. So I can get the ultimate boundedness, existence of theta star, and good variance results with that as well. And I like this. I think it's better than Q learning. I find it's numerically better behaved, I think. But I don't know why. Yep. Oh, what's that? I don't even know what that is. Is that when you actually manually? Oh, sure, yeah, because you get the same vector field. You get F bar would be unchanged. Yeah. But again, I just want to say this really loudly. It's a convergence. I don't have that yet. I mean, as far as I know, and I know this is not possible, but as far as I know, there's like a periodic orbit, that the mean vector field, mean flow, goes down to this compact set and then has a periodic orbit. I know that's not possible, but yeah. Oh my God, I'm sorry, if it converges. Excuse me. Excuse me. In the convergent case, if convergent, I'm so sorry. I just, like for Watkins' algorithm or for binning, those are the two cases where you have convergence. Oh yeah, or for what's called linear MDPs. any of those cases where you have convergence, then you end up with this horrible bound. But just by changing your objective, you make the variance bounded. Okay, so we were joking about the deadly triad last week, and it's so funny because for me, what's deadly? The deadly is the horrible, ill-conditioned nonlinear dynamics, which results in this 1/1 minus gamma here, and the variance, which can be so big that everything's meaningless. So I don't know. Depending on how you look at a problem, you can see different curses. And I didn't get to talk about it, but the second order methods are all I ever use. My models are not that big a dimension. And so inverting a matrix of dimension 100 is no big deal. And you get it's worth it. I would do anything to throw away this projected Bellman-Hill equation or figure out what it means. And there's linear programming techniques that I've tried to use instead, where there's more understanding of what the equations mean. So far, it's not, I wouldn't recommend it, the efficiency issues and stuff, but it's a possible path. Here's a really funny joke for you all. In ZapQ learning, or stochastic approximation, you need this Jacobian of F bar. And if you have a policy which depends on the parameter, there are two terms. There's this thing here, which is what I define to be A of theta. But you end up with this funky thing. What this is, it's the derivative of this with respect to the subscript, pi theta. So you get this thing here, which is what's called the score function. And you get this thing here, which is a solution to Poisson's, blah, blah, blah. It's some horrible thing. You'd have to use Q-learning to estimate that thing. I won't define it. Now, I've never bothered. I just use this approximation. I approximately estimate that. And it's brilliant. It kicks ass. And why? Why can I get away with that? Why can I ignore this term, which is potentially very, very large? Really, really fascinating. So another open topic. I don't want to do it. It's just the variance of estimating this is too big. Well, that's what this is, really. Oh, yeah, no, it's all this pretty theory of actor-critic methods and Schweitzer's sensitivity for. There's this theory where you can avoid that. I could show you later. But this comes from some theory from the 60s, which is the basis of actor-critic methods in RL. I could show you, offline. Yeah, and then there's other acceleration techniques besides. So people get angry when you talk about inverting a matrix. How do you avoid that? There's one thing that I jokingly called Zap Zero in the book, and there's improvements recently you can find there. And so Zap Zero just doesn't have a matrix inverse at all, but tries to emulate this. There's something that sort of looks like Newton-Raphson, and it's not. And empirically, at least in some cases, it works really well, even without no matrix inverse at all. Very, very low complexity, and does almost as well as Zap. Anyway, but that's a big fun. That's something fun for nonlinear control types who like to play with nonlinear control, because algorithm design is a control problem. We're trying to solve a root finding problem, and we have an ODE, and we want to put in feedback loops to get nice robustness properties and stuff. So, and this Zap Zero is an example of that. I take the D-dimensional ODE, make it 2D, and blah blah blah. I get some nice, nice results. And that, I think, is it. Yes, it is. Thank you for your attention. Okay. No, not to mention it. I mean, no. He had an oblivious policy, and I'm using epsilon greedy, and I find with epsilon small enough, I get stability. That's what I proved. Yeah. No, there's no dimension reduction. Oh no, my only point is that by using, see, Bard's example had epsilon equals 1. So in fact, I'm taking his input, his random, or variation of his distribution for training. And if epsilon's 1, it's unstable, as Bard showed. But if I just go through and I put in this smooth approximation epsilon greedy, it stabilizes. You know? And you can imagine making epsilon small and small and small, you do better and better and better. But what happens is you get an incredibly ill-conditioned problem, because epsilon equals 0 is meaningless. Yeah, 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 yeah. Oh, actually, no, I'm sorry, for epsilon greedy, it's meaningless. For this, it might be fine. Epsilon equals 0 might work, because this is already this Gibbs policy. You know, if I put here the deterministic, truly Q-greedy policy, then as epsilon went to 0, you think things blow up because it's numerically so conditioned. You know? You'd get a 1 over epsilon here if I didn't have that the Gibbs thing, the smooth approximation there.
This is weighting gamma and find smooth.
Yes, it's a horrible function I have. In the book paper, I have a formula, and it might be 1 minus gamma squared or something. I don't remember. I'd have to go back. I don't think there was that much, But then I would never not do this, So and unfortunately, I didn't have space to talk about it, But epsilon will not depend on gamma if you do this, and you might get some really clean lower bounds, I mean upper bounds, yeah. So that's a research topic as well. Oh yeah, yeah.
Thing that you don't like.
Oh yeah, sure.
In practice, people use clipping. Most things are, if you don't use clipping, they're unstable. Suppose you clip, and we develop stuff that might be still stable and then works.
No, but clipping for actor critic I've seen, but for this,
one could clip, say, or the increment that you do to your data.
Yeah.
Clip that.
Well, no, but oh my God, it's terrifying. You see, here's the thing. Well, yeah, if you clip by something that blows up, because remember, I've got my mean flow. Like in the tabular case, for example. So, so in my case, I have this until this gets too small, and then it's no longer true. I get this exponential convergence to a compact set. In tabular, you get convergence, so you have this. So you get this exponential asymptotically stable. If I bounded this, then I'd be crawling. I'd be going at a bounded rate towards the origin. It would screw everything up. If I had some way of clipping the noise and not the flow, So for example, if I had something like this, if I had, excuse me. If I had access to this and I could clip the noise, yes. So now, it might introduce some bias, but reduce variance and things like that. But I want to keep the linear growth rate of the mean flow. No. All right. Okay.